this is joint work I've done with my former student Saman and Mariano when Saman interned with Mariano at Intel Labs, and as Elvin alluded to, and again given Antonio's introduction, I can follow up on that and then look at learning structures that have a particular properties. Moving beyond undirected graphs, we're going to look at directed ones, and then a particular constraint on acyclicity, which is kind of key in several models that we use for causal representations and beyond. So this I can basically skip, and that's what Antonio has served already, and then that's nice. I can just jump into what I'm going to be talking about today, and then I said, the goal is, given data that we observe, like typically passively, and I'm going to describe that as observational data, then the goal is to learn the structure of one of these creatures, right? Which is a graph that particularly see now there's arrows, so it's directed. And then also importantly, it's acyclic, right? So there's no cycles there if you follow the arrows. Those are DAGs, which have been, again, prominent elements for a while in what we call, again, Antonio was describing a lot in the context of graphical labs, so like Markov random fields. Those are instances of undirected graphical models. Now, the focus here is on Bayesian networks, okay? These are probabilistic graphical models where you have directionality, and then DAGs are at the heart of those. And those are used to encode conditional independences among random variables. Let's say each of these nodes can be viewed as a random variable, and we want to encode those probabilistic structures in a particularly tractable way that factorizes. And then DAGs are also quite important in that context and beyond, because they can have a causal interpretations under some assumptions, in particular when there's no latent variables, then you can see like these structures are saying that this is the direct cause of this particular variable when there's a direct arrow connecting it and so forth. And hence, lots of applications, right, in biology, genetics, finance, and beyond. But well, in dealing with these particular graphs, there's very unique challenges that makes it interesting, but kind of a lot of progress was, I don't know, has eluded people for a while because of, again, the issue of directionality, fact that we have objects, right, like adjacent matrices, and symmetry gives us a lot of nice properties. That breaks here. Most importantly, acyclicity, enforcing acyclicity in a graph as we're searching over graphs, right? The best one that's a cycle, well, that's a combinatorial and notoriously hard constraint to enforce. And also, when it comes to learning these graph structures from passive or observational data to be considered with interventional data, where we can actually act on different nodes, that can give rise to a lot of interesting identifiability issues. There might be a lot of graphs in a way that could be compatible with the joint distribution of our data. So then that's the problem there of finding a unique structure might not be well posed, and then the people have studied for a while under what conditions that's possible. Okay, so then just a parenthesis, while this talk on our particular work is going to be mostly on how optimization theory and statistical learning can aid inference of causal structures, and that's important. I think maybe the broader perspective, arguably, it's more interesting and potentially looking ahead has further ramifications. And that's exactly how can causal reasoning, right, inform how we do machine learning, in particular in frontier topics, right? There's, again, causal models, we're going to talk about structural equation models. Those are richer structures than joint distributions. So basically, whatever we look at associations, right, in probabilistic statistical learning, especially when you want to change mechanisms, right, then dealing to out-of-distribution generalization or distribution shifts, transferability generalization, and then there's a lot of interest now in kind of using the tools of a causal reasoning. There's been a lot of progress on how to make the mathematics of this more formal in a way. And then here are some representative references, books and tutorial papers, which I've liked a lot. If you want to learn more about that, this is a great book with a focus on signal processing and information theory. Bernard Skolkoff involved there also in these proceedings of the IEEE paper, looking at this stuff. And I think he gave a plenary talk in one of the recent ICAST, kind of serving that work. Here, more applied, but again, high impact work on how and what Michaela van der Schaar calls causal deep learning, a lot of applications in healthcare and health informatics. So then lots of interesting things to look. Now, where, given a causal model, given the causal structure, then we can use this to reason, right, when agents interact and so forth. then as how can this affect how we do machine learning from semi-supervised learning beyond. And of course, I see you taking photos. This is very small. I'll be happy to share the slides so then you can look at these things if you have any questions. But then I'm not going to be talking about this today, but just to give you this broader perspective, because I think this is very interesting. And I've been trying to encourage my own students to get into that. And hopefully something coming up soon from our group. So today, I'm going to start talking about first giving a background, and maybe that's all I'm going to be able to cover in half an hour, which is what I have, I guess, and then that's perfectly fine. A little bit of a didactic introduction to the problem of learning DAG structures from observational data. I'm going to focus on score-based approach, and then this is not to be confused. If you do diffusion models, people talk about scores as the gradients of logs of densities. This is kind of just a feeding term, but people call it score in this context. And then, yeah, if I have time, I'll tell you a little bit about what we did, our approach, which we call the concomitant linear DAG estimation. That's collide. And I'll tell you more about that, its performance, some conclusions, but most likely I'm just going to cover the first part, and that's perfectly fine. And hopefully you will learn something from it, and I'll give you some highlights of what we did. So, there's questions, but there's been questions already, but obviously at any point, just feel free to interrupt me and I'll be happy to explain. Let me set up the problem first. Objects which are going to be here first are two. One is this latent graph of interest, a DAG. We encode the topology of it in this adjacent matrix W, okay, a D by D matrix of H weights. Columns, right, are encoding, for example, the jth color W, the jth column Wj is going to encode the set of incoming connections to node J. Why? Because entry Wij is going to be non-zero whenever there's a directed link going from I to J, right? So then the second index, the column index, is the target node, right? The first index is the set of potential parents, let's say whatever is non-zero. So you see here W24, W14, W34, all those three are non-zero. These are the direct parents or potential causes of node 4, okay? And then that's my matrix W. That's the first element, right? A DAG, and then an important property of directly cyclic graphs because of again, its directionality and so forth. There always exists, those DAGs induce what's known as a partial order on the node. So that you can always order them. And then here I order them according to that, like 1, 2, 3, 4. So there's always connections, let's say, going from a number to a higher one in this case. And that's the case there. Now, the other important object here is this random vector X, a collection of D random variables, one per node, right? And here's where the link is coming, right? I'm going to assume that the joint distribution of the variables in that random vector satisfies what's known as a Markov property with respect to the underlying DAG. Okay, so that connects the distribution of the random variables to the graph itself. And then what do I mean by that? Well, that the graph itself is going to encode a collection of conditional dependencies or independence among the random variables such that we assume that each of the variables xi's is only going to depend on its parent nodes as encoded on the DAG. Okay, so then the joints can be factored on conditional marginals where each variable in a way depends only on its direct parents. Okay, and then that's that Markov property. One way to generate such distributions is through the class of structural equation models. I'm going to focus on the linear version of it, the simplest possible case here, where an SCN specifies a collection of D structural assignments, one per variable, where we say basically that Xi, the random variable, is a linear function, right, of all other variables in a way, but look that this depends on that I column of the density matrix, which basically it's encoding the direct causes, right, the direct connections on the DAG. So what I'm saying here is that Wi is going to depend only on its direct parents, right? So this assignment plus some exogenous noises, Ci, one per variable. And then crucially, we need to assume that the collection of noises in a vector Z are mutually independent. Okay? Otherwise, you are introducing dependency. So then the noises have to be IID across variables. That's fundamental. So then that gives you that Markov dependence. And for example, X4, right, is W4 transpose X plus Z4, which means that X4 only depends on nodes 1, 2, and 3 as the DAG specifies, plus some noise before. Okay, so that's a linear SEM. One can have nonlinear models where you could have a function here, right? Arbitrary, not necessarily linear, but we'll keep it simple for now, for today, actually. Sounds good? So the problem here is, suppose we have a data set X of n IID observations of that random vector X. I collect this in this D by N matrix. Remember, D number of variables, N number of samples I have. Can I estimate the adjacency matrix of that graph? Again, only from passive observations, namely realizations of that joint distribution P of X under these modeling assumptions. So the class of score-based methods, and there's also constraint-based methods that I'm not going to be talking about today. I can describe more of that afterwards, but I'm going to focus on this here, is as follows. Given X, adhering to some linear SEM, we want to learn this latent DAG that belongs to the family of DAGs by estimating the density matrix as a solution to the following score minimization problem. Notice, again, I'm searching over the space of DAGs. Okay, a combinatorial problem that makes it pretty tricky. Look at the constraint over there, right? So, and the goal is to minimize this score function S, which is in a way a data fitting term. I'm going to use the linear SEM model there, of course, maybe use least squares. And the idea is to search over graphs that gives me the best fit to the data in some sense. Okay, and then that's the idea. This is an NP-hard problem. This is well understood in general. Of course, the main challenge comes from this acyclicity constraint, which is very nasty to enforce. And of course, there's issues of identifiability, as I mentioned, again, lacking potential interventions to single out maybe ambiguities. Under some cases, this problem might not be identifiable. Like, for example, if you have a linear SEM where the noises are Gaussian, but the variances across variables are different, well, in that case, it's not identifiable. When you make it nonlinear, the SEM, then typically the problem becomes better posed, but then estimation can be more tricky. But anyway, similar to like when you do ICA to try to identify multiple sources in blind source separation, these are results of similar flavor. Now, how can one tackle that formulation over here, how this has been classically looked at? Well, one has to resort to combinatorial search methods. Okay, for instance, typically one assumes some parametric model for the distribution, and then one looks at some penalized likelihood type of approaches, right, using BIC, MDL, or some Bayesian scoring functions where you put some priors on candidate DAGs. And again, there's various approaches to that end. Now, as you might be thinking, and that, again, it's indeed true, this is very challenging, especially because the space of DAGs grows super exponential in the number of variables. Maybe there's 500 DAGs on 4 variables, but then over 10 variables, the number of DAGs you have is a digit with 20, it's a number with 20 digits, right? So then this is sort of crazy. And then, of course, many of these combinatorial methods face scalability issues. Addressing that, people have proposed greedy type of approaches where you maybe are looking at any given point in your procedure, you are maybe have a candidate DAG, and then you are considering neighboring DAGs, and then how you define those neighboring DAGs depends, but typically is, again, other graphs where you potentially are adding a connection to another node, one way or the other one, or moving an edge. So these are kind of nearby DAGs. You can evaluate your score on those. If you make an improvement, you move there, blah, blah, blah. And then some of these approaches have guarantees to some, again, local optimal solutions. Also, what has been widely looked at are what are known as order-based methods. And then what do I refer by those? Well, maybe, again, going back to what I mentioned early on, right, DAGs induce a unique partial order on the variables, right? And that's explicitly mentioned there. If I knew that order, that causal order, then, okay, and I order the variables accordingly, like from top to bottom, then W is always upper triangular, right? So then if I knew the order, I can just focus on that upper triangular part. And the problem boils down to a classical variable selection problem. I just need to find the sparsity pattern, what's connected to what, but then the problem is clearly much simpler if I knew that order. The problem is that I don't know that. But again, thinking it that way, one can parameterize DAGs, or namely the adjacency matrix of any possible DAG in the following form, right? Where pi is a permutation matrix that encodes the causal ordering, and then U is an upper triangular matrix. Okay, so then the adjacency matrix of any DAG basically can be written that way. What I'm saying there is that, okay, there exists a permutation that makes your adjacency matrix an upper triangular matrix. And that hopefully it's clear, right? So then one could then instead try to, okay, implicitly, right, or explicitly actually enforce the constraint by searching now, instead of over W, optimize over pi and U jointly to some extent. That's perfectly fine. Of course, the problem is still hard because, as you know, searching over permutation matrices is still a combinatorial and hard problem. There's been some progress very recently, as you can see, in terms of searching over exact DAGs in an end-to-end differentiable fashion using different types of smoothing or approximation methodologies to search over this Birkhoff polytope or permutation matrix, or also maybe searching over orders, right? You have to search over in which order the variables are. So then that's a search of what they call the paramethahedron as well. But again, regardless, there's many recent angles to tackle the problem in this way. Some people have looked at bi-level optimization, right? Where, for example, you do topological order swaps at the higher level. You basically reorder variables. Given that, then you try to estimate the U matrix and then repeat. That's fine. And there's lots of interesting work and a lot of impetus actually recently. But still, what we have found, and others as well, is to accurately recover, again, the causal orders can be very challenging still, especially when the data are linked. And then that's has prevented a little bit progress in this set of works. And let me tell you what has been, I believe, a very nice idea leading to breakthroughs in this field. And then I wish I heard about this earlier. Okay, so this is the work from 2018, groups at CMU led by Eric Shin. And then their different approach, instead of tackling the problem again combinatorially, is to introduce functions which are non-convex but smooth, that's DAG, to somehow characterize acyclicity. Okay, functions of the adjacency matrix, okay, whose property in this particular case is that their zero-level set corresponds to the DAGs, adjacency matrix of DAGs, namely that H of W is 0 if and only if G of W corresponds to a DAG. Okay, and then I'll stay at that for now. But if we had that, then what's the nice upshot or impact of this is that I can transition, right, from combinatorial search algorithms to non-convex but smooth continuous optimization, right? So the problem on the left over here is the one I talked so far. It's a search over a space of graphs, inherently combinatorial, nasty, and empty hard. Well, this is still going to be hard, but what I'm doing here now, right, I'm searching over adjacency matrices, okay, just matrices in R D by D. I'm trying to minimize my score, and then here I'm using an abuse notation because clearly I'm calling both of them S, right? But then one, its argument is a graph, here it's an adjacency matrix, so that this is not the same score, but it's trying to capture the same thing, and subject to this constraint. And again, if I'm here on the right-hand side, I can rely on gradient-based methods, whatever optimization algorithm you like, potentially to solve this equivalent problem, which of course is going to be hard still, but we have other machinery to try to search, especially now in the era of machine learning, deep learning, where we can just try to tackle any problem. We just don't care about convexity too much any longer, right? So then smoothness is important, but hopefully you can appreciate that. And if we have those functions, one can really change the perspective as to how to tackle this problem, which I think is a very cool idea, okay? Which again, I wish I knew before. So let me tell you about what are these cyclicity functions? Like, seem too nice to be true. Do these exist? Are the unicorns or whatever? Let me show you about a little bit about those. And then also, I haven't talked too much about the other ingredient of the models, which are these core functions. And that's where our contribution in this work pertains to. But let me just tell you what people are dealing with so far. Okay. So far, so good. Makes sense? Awesome. So then, this DAGs with no tiers paper back in 2018 proposed one first such function, a characterization of cyclicity, which is based on the trace of the matrix exponential of the JC matrix minus D. Okay. Notice that the argument actually of the matrix exponential is not W, it's W Hadamard W, entry-wise product, because again, graphs in this context could have positive or negative weights. That's fine. Typically, you have maybe a causal effect, but could be activation or repression. So then the sign, meaning having different signs potentially, is really something meaningful. And we're going to get back to why would we like to make everything positive in a second. But the basic idea is that diagonal entries of powers, right, of the J's, if you think about W, W squared, W cubed, that's capturing, right, number of paths you have in your graph of length 1, 2, 3, and so forth. Okay? And if you look at the diagonal of that, those are paths that start the node and then finish in the same node. So then that's what we call cycles, obviously. So then looking there through the trace could hint as to whether there are cycles of any length or not. And again, you know, the matrix exponential has a series expansion, right? So then it's looking at all those powers. So then if you look at what e to the W is, okay, it's the matrix exponential, is defined in this way. And here you have a toy graph with 3 nodes and then cycles of length 3. You have the identity first, which has some spurious ones. In this case, D equals 3, 3 ones. So if I do the trace of that, I don't care about this. That's why I do minus D over there to cancel that 3. And then I start looking, are there self loops? Well, diagonal is empty. Are there cycles of size 2? Diagonal is empty. And then I start to see entries in this case at the third power because I have cycles of length 3. Okay, so then if all these diagonals are empty, except obviously the identity term, then that's gonna be 0, if and only if there are no cycles in the graph. Okay, and anybody now? And the example here, right, was with binary weight, so there's no need to do W Hadamard W. But anybody can tell me, why do I care about actually making this positive? Why do people look at W Hadamard W and then apply this function?
Actually, I know the answer because it's actually some product of, if it's positive, it's some product of positivism, and you plus them, and you but if you have negative, they can cancel each other to get 0.
Bravo. Exactly, right? Suppose I have, I'm meaning what powers of the density matrix are actually, even in the weight, in the positive or negative weighted case, what it's doing is you sum over paths all those weights, right? And then you check whether they're 0 or not. That's what's coming. So then you can have cancellations, right? Potentially, maybe things can cancel out here if you have different signs, and then you might miss that cycle, right? Then it's going to be a 0 on powers of the density matrix, but indeed there is a cycle there. So to avoid that, we make everything non-negative. Doing W Hadamard W preserves the support, right? So that you're not changing the sparsity pattern, the cycles themselves, but then you avoid that potential cancellation. Clear? So then notice that the non-convexity of this function, right? That's a smooth function, is non-convex. One can show it's going to be 0 if and only if there's no cycles in the graph. But it's non-convex because of the W Hadamard W. Yeah. Sounds good? Yeah. Question?
But in that sense, isn't it then better just to look for positive weights and just say e to the power W, and if that's causing your non-convexity? So
yeah, well, yeah, exactly.
That's find it weird to have negative directed and negative weight. What does it mean? I mean,
no, meaning suppose I'm a variable or whatever. Meaning I could be affecting you, right? But then it could be in a negative way. Meaning that drives the correlation, right? So the meaning I'm affecting you, I'm driving this correlation, let's say, beyond that. But then the moment I grow, whatever that is, then maybe whatever you're measuring that variable goes down. That really can happen, and it's very important to have those effects. So yes, and as you said, we're working with Samuel now, and then what if we assume many DAGs actually could only be non-negative, let's say, and in that case, then all this is going to be convex, and I don't know why, surprisingly, people have not looked at that. Because again, in machine learning, they care mostly about smoothness. You can do, again, backpropagation with gradients, but then convexity or non-convexity, they don't care for some reason. But then there's a lot of nice things you can say if you have a convex problem, and then we're looking at that. Now we have an upcoming paper in ICAS as well. So, question, please. Good question, indeed. We were thinking about that as well, and the answer comes along the lines of what we're saying, right? Indeed, you could do that, but then you have a non-smooth cost, and then people care about having smoothness to run gradients and what have you. So in that case, this is okay. With absolute value, you get a convex objective as well. That's fine, but this non-smooth, and then again, I haven't asked people, and people haven't commented explicit on that, but that's what I believe is the case. But you could do that as well, and we're looking at that with Samuel as well. Yeah.
Taking this automat is increasing the value of the weights, right? In some sense, and because when you're optimizing this objective, this might not go to exact zero. You know, you might not be able to optimize it perfectly, but you might have some cycles. But taking this automat wouldn't exaggerate the value of, the value that you find for this function.
Well, meaning depends, right? In general, yes, but I would argue if you have weights between 0 and 1, it makes them smaller. So meaning you can have both things in general. I agree, and again, I describe this as a first function. There's been other functions proposed to follow up in a way, looking at specific properties as meaning in practice, how strong the gradient signals are that these things generate. So then kind of empirically, people have looked at those and they're more motivated, but meaning things can go both ways. As you say, in some cases, things could be more desirable than others, but in practice, this works well. And again, we're wondering why things like in convex settings or with absolute values, people have not looked at those. But again, you can optimize things better, but for the most part, the issue is that you want to have gradients to then learn these things. Now those are good points. And I said, to speed up computation, we have proposed this polynomial version of it. And again, we know, right, like as Antonio was mentioning, with filters or polynomials like K-cap, we're looking at D by D objects matrix here. So then any of those can be reparameterized as a polynomial of at most order D on W or W has W. So then all of these are kind of instances of the examples I saw before. Recently, in this DAGMA paper 2022, they proposed a different log depth acyclicity characterization based on the fact that DAGs are nilpotent, right? Again, upper triangular, all their eigenvalues are 0, so the spectrum collapses. And basically, one can look at this a parameter S in this function, but you can look at D log S minus a log depth. Again, log depth, typically we think about it as well defined on the positive semi-definite cone, right, of matrices. Well, here we have adirectionality, so then that's a problem, and then one has to be careful where this is defined. And in particular, they look at what's known as the set of M matrices, where again, this will be well defined. This works, and then one can show that that acyclicity function has some nicer properties, and I would say state-of-the-art methods rely on this. For example, if you look at the series or Taylor expansion of all of these functions, right, notice that then if you're looking, maybe you may have long cycles, right, and you're trying to minimize or penalize with this, well, K factorial becomes large, then kind of large cycles are really down-weighted. You might miss those. On the other hand, if you expand the series expansion of this, again, function over here, well, the weights of longer cycles then are going to be kind of, this has heavier tails, so then this doesn't heal those cycles so fast, so then it's better at potentially removing those longer cycles as compared with trace exponential and beyond. And again, it has nicer properties in terms of the gradients. All of these functions have a very well-defined closed form gradient. It might require inverting a matrix, so then complexity of this approach is cubic, but anyways, one can work with those. So, 2 more slides, and I think we can wrap it up. What have people dealt with in the context of, or chosen in the context of good score functions? Well, as you might imagine, again, focusing for now on linear SEMs, People have looked at ordinary squares cost, trying to match X, my observations, to the predicted values, right? W transpose X. Of course, most graphs and DAGs might be sparse, so then we can penalize with an L1 norm as well in the symmetries, where lambda is a tuning parameter that controls the edge sparsity. People have shown a lot of desirable properties, again, in the field of Bayesian network model selection, computational efficiency, robustness to, again, misspecification of noise distributions. Even consistency can be established in this work, even if you don't have the L1 norm penalty. So then kind of a lot of nice properties, of course, coming with least squares, as you might imagine. For people more in statistical signal processing, coming from, again, sparse recovery and the like, once you see that criterion, right, then, well, this should ring a bell. This is what people call multi-task lasso, okay, where you have, instead of just a response vector, you have a matrix, right? The columns could be different tasks, different measurements, right? In particular, here, the response and the design matrix coincide. So then I'm trying to auto-regress X to X, right? And then, well, typically you have Y equals H times W. And this has been well studied, and we know that the optimal minimax rates call for choosing a lambda of this order, where sigma is the noise variances, right? And then you have square root log D over N. Naturally, if you have more data, more measurements, N, then you are prompted, right, to rely more on your data fit rather than in regularization. Otherwise, you have a stronger pool for sparsity, for instance. But of course, all that's nice. You should select lambda the way. The problem is that the noise standard deviation or variance is rarely known, right? So then we don't know sigma. How can we go around that if we want to pick lambda? Of course, we can do cross-validation, what have you, but then that might be an issue. Then some key limitations we identify, which motivate our work if you select this type of score functions, right? That, okay, this will call for just retuning lambda every time, because again, assuming we don't know the noise variance, that's typically the case, right? Well, every time you change a setting, a different mechanism, the noise variance might change. Well, you have to do cross-validation to select your lambda, on and on and on, which in some cases it's fine, but then the question is, can we try to cook up a new score function that in a way makes it noise adaptive? Okay, so like maybe by estimating jointly W and sigma, if we can embed that into the process, can we in a way try to make the selection of lambda independent of sigma? Can we remove lambda from there? That would be nice, and that kind of hints to noise adaptivity in a way. Also, if you look at this cost function over there, even if you knew sigma in a way, this is implicitly assuming that the noise variance across all noise variables are the same, because otherwise we should have to do a weighted least squares criterion, right? Like we have to do the diagonal matrix of noise variances, pre-multiplying that over there just to kind of compensate for the different noise variances. Otherwise, ordinary squares is going to be a biased estimator, right? So then in a way, it's assuming we are in the homoscedastic setting where all the noise variances are the same, but in many problems, one has, like again, different uncertainties at different variables, so then one has to consider the heteroscedastic case. So then again, that does not account for that. So moving on, what we did in this work, and with this I can conclude for today, is that we proposed a new score function that is convex, okay, for sparsity-aware DAG learning. We incorporate what's known as concomitant or joint estimation of scale parameters. Then our goal is to learn both W, the DAG structure, as well as the level of noise, the scale, okay, W and sigma, in a convex fashion. As the result, collide, which is again a short name for concomitant linear DAG estimation, decouples lambda and sigma as we wanted to achieve. So then that makes it noise adaptive. There's no need for recalibration because you are kind of automatically compensating for different sigmas, even as you change different settings. And again, unlike ordinary squares, because you are estimating the noise, this allows to deal with the heteroscedastic setting in a way. Even if the noises are unknown and even different across variables, we can estimate all of them along with the DAG structure and then in a way adapt to those different, more challenging settings. So then Collide outperforms state-of-the-art methods. We have the paper here if you want to check it out. We have done million experiments. Some of them are just here, and I'll go over that in a second. Across different types of DAGs, Airbus Reni, scale-free, there's many that people, again, there's a lot of work in this area recently, so then there's a lot of very well standardized experiments one should run across different types of graphs, across different types of noise distributions, Gaussian, exponential, Laplacian. So our method is fairly robust to those, especially when the DAGs are larger. You can go all the way to thousands of nodes, again, using these first order continuous optimization methods. And even when the noise level profile is heterogeneous, most prior approaches, again, that use ordinary least squares, whenever you change the noise variance, they basically become biased unless you do, again, parameter fitting very carefully all from the beginning. And also we find that the method is fairly robust and stable, showing much smaller standard errors across typical domain-specific metrics. What you typically compute here is what's known, for example, as the structural Hamming distance, okay, which what you're looking at is you have your ground truth DAG, let's say, and then how many you are counting, right? How many errors you make in your estimates to the ground truth in terms of missing edges or kind of directional flips and so forth, and you count those normalized by the number of nodes you have. This is the structural interventional distance, which basically says in the graph you estimated how many causal paths you blocked, for instance, false the discovery rate, true positive rates, blah, blah, blah. And here is just, again, some results where we compare our approach, Collide, non-equal variances, equal variances, then equal variances when you have the homoscedastic setting. That's the variation when you have potentially different noise variances. So you're estimating more things, basically one noise variance per node plus the whole DAG. And state-of-the-art approaches, Golem, which assumes a score function, assuming that the noises are Gaussian. So you use a profiled log likelihood score instead of least squares. In that case, Dagma is using an ordinary squares with this fancy new log depth criterion. And here again, for 200 nodes, Erdos-Renyi 4 graphs, DAGs, that means that they are Erdos-Renyi DAGs with the average degree equal to 4. And people, again, over all the experiments and all these prior papers, they found this to be kind of the more challenging setting in terms of edge density. Here's for equal noise variance, homoscedastic Gaussian noise. But again, most of these words using least squares, they just, again, assume that the noise variances are all equal to 1. That's the setting over here, where we are even performing much better than them. But then once you change the variance to 5, right, then they suffer big penalties while we remain fairly robust and doing much better. But that's, again, I haven't told you at all what we are doing here, but I think it's fine to wrap it up with these results. Of course, the second part of my talk tells you a little bit about that. But I think it's a good point to wrap it up. Hopefully, I've told you enough about the idea and what's the work